This is a demonstration of how we can reconcile a gene tree and a species tree just using Mega. If you'd like to follow along with the Mega software, you may have it installed from some of the previous worksheets. That's fine. If you don't want to follow along with Mega, that's okay too. You can just follow along and then take notes or make a note of anything that you might have a question on. So in this example, we've got 4 species, and in those species we've identified different numbers of genes that appear to be homologous. Now, when we say homologous, we mean they're in the same gene family, and so anytime you have 2 genes or 3 genes in the same individual, it's obvious those are paralogous. Those are gene copies. That's why they have more than one in the same genome. But when we're trying to compare between species, it's more problematic. And there are many different ways that we could potentially end up with this number of genes, all starting from one ancestral gene. So I'm going to draw a line down here, a beginning line, as an ancestral gene. Now, we're going to have some duplication events. Let me just give you one possible scenario. So it's possible that we had a simple gene duplication early on that led to one of the genes in this gene family. Okay, so let's finish drawing that out. We'll leave it black. Okay, and then a second one, and let's make this one a different color just so we can keep track. We'll make this one green. Right, the second copy of the gene is why we have the second copy in each species. Let's make that a little bit closer. There we go. Oops. And then another gene duplication event here, more derived and a more recent one, and we'll make this one yet another color just so that we can distinguish this second one. So the way I've colored this, and this is a convenient way to do it, the colors represent orthologous gene pairs, right? Genes that can trace their history back to a speciation event rather than a duplication event. And then when we switch colors, that's when we get into paralogous gene copies. Now notice that this really elegantly explains with just 2 duplication events what the history of these genes were. But realize that when I draw this internal phylogeny, that is a gene phylogeny that we put onto a species phylogeny. And so we could actually draw each of these out. In fact, let's color code these just so it's a little bit more clear. I'm going to give these a color that's close to at least the lines that we're doing. Okay, so let me do this. So we'll make those 2 kind of that purplish blue color. We're going to make these 3 green. Oops, that one, and that one. Okay. So there we go. And so now I need to make this one green also. So now we've got this kind of color coded, and notice that if we kind of unwrap the gene tree that's inside of this larger species tree, we have our own phylogeny of all of the genes. Okay, so we've got the 2 purple copies that are very closely related to one another. I'm going to do a little sketch of that. So we've got here and here, right? And I'm just going to do this in blacks because this is we'll make all of them the same. Okay, so here, let's do it down here so we have more space. Here and there. There we go. Tree's probably going to be a little lopsided, but it'll be easy to read. So that represents those 2 blue ones. Now notice that they are most closely related to these 2 copies of the green gene in the mouse and the human. So this node right here, put a little square around it, that represents a gene duplication event, right? It's this same node right there. So all I've done is kind of unpacked, undrawn those nodes there. So this is, and if we wanted to put the gene copies down there, we would put one here. Oops, let me get a, there we go. So having trouble there grabbing it because it's a little small. But that one and that one represent those two blue copies. And then this one and this one represent those two green ones. And then I've already got the, there we go. I've already got the gene duplication event here. So I've drawn everything above here. Now notice if we go down one step farther, we have the next closest one is the lizard that's got this green copy. So we'll draw that one down here. So there's the green copy from the lizard. And then the next closest one is the green copy from the fish. Okay. So we'll just put the little green ones there. I'm not putting species designations on here, but we could if we needed to. There we go. Sorry about that. Okay. But we still have the black lines to do. And so then if we go even farther down, right, and so each of these nodes, so that node right there, which is a speciation event, is represented there. That node is represented there. That node right there is represented there. So these are all speciation events. There's our one duplication event. And then we have the other parts of it, the black part of the phylogeny. Let me just do this. So we've got down here, I'm going to make a little bit more space so we can work with it again. It's going to be a little lopsided, but not too bad here. So on this other side, we have our fish species. And then coming off of that, we have our lizard species. Actually, it's a little easier to do this backwards. So this will be the human species. The closest of the human species is the mouse species. And then we have our lizard species. And then we have our fish species for these black genes. And so I'll move these again. We haven't labeled the species and we just used color codes, but I'll move them here so you can see as we go. I think if I hold down Control Shift, it'll make a copy of it for me. Oh, didn't do it. We'll just do this. Okay, so that's the one from the human. Here, since we don't need these up here anymore, maybe it's be quicker just to grab just the boxes there so you can see which ones are represented down here. Keep grabbing things other than the boxes. Those are small boxes. There we go. There we are. Okay, so this is our gene tree that we have now here mapped onto our species tree. Now, sometimes it's rather straightforward, and so we have speciation events at all of the nodes except for that one, and then this one here will make it a slightly different shape. Maybe we'll make it a little bit more of an elongate rectangle. And that node right there is represented by this deepest node in our gene phylogeny. Okay, and then all the other nodes, so this node and that node represent those two nodes right there. Right, the next one up, that one and that one represent those two nodes. And then we have three nodes right here that are represented by that one, and that one. Okay, now that's one way, but there are other ways that we could potentially end up with that. So for instance, maybe this gene duplication could have been a little bit earlier and then we lost one of the copies in the lizard. If that was so, then these genes, these bluish purple genes, would have different relationships in our gene tree. So the key to all of this is being able to map a gene tree onto a species tree. Now, I don't care that you are able to do that. In fact, it's quite technical and complex by hand. It's really tricky to do. But I do want you to be able to recognize it. I'm going to show you how Mega does it, just as an example. But I do want you to be able to recognize that if we had a phylogeny like this, if I gave you the species tree and the gene tree, you should be able to unwrap, so to speak, pull out the gene tree and then recognize which nodes are duplication events and which nodes are speciation events based on the mapping here on this larger tree. So let me just demonstrate quickly how Mega does this with an example file. And again, if you'd like to, you can follow along. The files for these, when you download Mega, are in the documents portion. If you have on a PC, it's documents, Mega X, and then examples. So documents folder, Mega X, examples. If you're on a Mac, it's in your home folder, and then Mega X, and then examples. Okay, but if you don't want to follow along, that's fine. You'll see I'm on a PC, so I'll navigate here and you'll see this. Okay, so the first thing that I'm going to do is I want to do over here user tree, and I want to find gene duplications. So it's got several steps that we need to go through to do this. The first thing we need to do is load our gene tree. And this would have been generated with a large data set, but just for the genes that we were interested in. Maybe we have many other genes that we could use to figure out phylogeny. But we want just the ones that show the homologous genes in our gene family. So in this example, I've got this one just called gene tree, conveniently enough. Then we need to map our species name. So for each of these genes that we have represented, we need to tell what species they're from. And it doesn't matter what they are as long as you put the same name for each of these species. So for instance, I can do this. Human, maybe it's easier to cut and paste. And then that one's human. They're labeled already with the genus and species name, so it's pretty easy, right? So mouse, and mouse. And this is a pufferfish, so I'll just say fish for convenience sake. There's our other one. We only have those 2 copies of the fish gene. And then the lizard gene, we have 2 also. Nolus carolinus is these anal lizards. We get them around here. They're the green ones. They're not as common here, a little bit more common in hill country, but they're common across the eastern United States. Okay, so anyway, now we have all of our species named, all the genes assigned to a species. The next thing to do is to load our species tree. Now it says optional because it can calculate a species tree now that we've named them. It could calculate one for us, but usually it's a very limited data set. So hopefully we've got a more extensive data set that's given us a better estimation of the species relationships. And in this case we do. We've got an example here. It's called species tree. Okay. Try one more time. I don't know what that was. Oh, I see, because in the species tree there are different names. So let's come back here. I'm going to go back one step. Okay, let's start over. Sorry about that. So in my species tree, if I looked at it, my names would not match exactly what I put down. So this one actually has a little separate one that you can load in. So I'm going to do File, Import. And it is this one, Taxida species map. Yeah, so pufferfish, I think, was the only one I put fish instead of pufferfish, which is why I didn't like it. Okay, so now when I load the species tree, everything should be good. Yep, looks good. Okay, the gene tree was already rooted, so it skips that step automatically. We're going to root the species tree. So the species tree is going to be rooted right here to the pufferfish. Right, so we're going to root that. Should be already good to go. Say OK. And then we're going to launch the analysis. And it's going to do everything for us. Now, it draws this more spread out tree. And it turns out that based on those gene relationships, that the tree is actually a little different than we had inferred. So in fact, there is a very early duplication event. So in this, the blue diamonds represent gene duplication events. The red diamonds represent speciation events. So here we have the species that matches, just like we looked earlier, the fish, then the lizard, and then, of course, the 2 mammals. So that's one side of the tree, but notice it's a little bit more complex over here. We have a gene duplication event, and then a second very early gene duplication event, and then a gene that was lost, not present here, in the fish or in this other subfamily in the lizard. So this explanation is actually a little bit more complex once we look at the gene relationships. So that was just an example I did. I'm going to actually undo all these things here. Let's go back to our very original genes. And so once we have mapped them onto the species tree, we actually see something that looks like this. We still have our first ancient gene duplication event. In fact, we can go back and say, well, here's that one half of the tree, right, which is the bottom of that gene tree that we were just looking at, okay? So that, the black thin lines that we just drew in there are indicative of this bottom half of the tree. But now we have this top half that's a little bit more complex, the ancient gene duplication event, and then another one right after that. So here's our ancient gene duplication event. We can build off of that. But then there is a second one that is right after that. So there's another one right here. And this is important because as we're looking at ancestors, how many genes did the ancestor of all these organisms had? Well, once we've mapped them on, we know that it actually had all 3 copies. And this says something different about the evolution of these, okay? And then what happened is, as we look at the story, that this gene was inherited by the lizard, and it still has it. However, when it was, sometime as it was passed down to the fish, that gene was lost. So let's put a little X there just to show us that it became a pseudogene. And we may even be able to still find it if it hasn't mutated so much that it's no longer recognizable. I'll just put a little X there to represent the loss of that gene in the genome. Okay? But the mouse and the human still have that gene. So we will connect those lines there. Here we go, mouse and human still have that gene. Okay? Now we still have this third gene to do. So in the fish, this gene was inherited. Oh, he went a little bit too far there. Let me just go a little bit shorter. All the way up to here. So the fish has that. But when it was passed down sometime after the lizard broke off from those other 2 mammals, it became a pseudogene. When extinct, again, we may be able to find it if it's still similar enough, but it's no longer used as a gene. So let's just do a real quick X there so we can mark that one as, there we go, lost. And then this one was inherited by the mouse and the human. Now we could color code it to make it a little bit better. One last thing I'm just going to say before, if you want to, you can go back and forth. So here, let's see if we can zoom out a little bit. Boom, 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 view. I don't know if it lets me zoom out. We might have to go up and down, right? So human, mouse, fish, right? So that represents this one right here, human, mouse, and then the closest relative, because the lizard one was lost, is that fish gene, okay? The next part of the tree shows human, mouse, and then lizard as most closely related. And so that is this second gene here, so human, mouse, closely related, and then the lizard, and then that one that's missing in the fish. And then finally, the entire other half of the gene tree that matches the entire species tree. And so we see that down here. So hopefully that's making sense to you. That's a fairly complex example, but not too bad. And in some cases, we'll read an example where it's very, very complicated with multiple losses and multiple gains. And some genes that seem to be subject to this that are more prone to duplication and more subject to the forces of natural selection where multiple copies might provide a benefit, they have an even more complex story. Okay. Now, the last thing that I want to mention are these gene names. Once scientists figure this out, researchers figure out what the genes are and what subfamily they belong to, they're often given names that reflect that. So we probably could have guessed this just ahead of time looking at the gene names. This work had already been done, right? So C6 are all orthologs of one another. They all are connected through speciation events. PRF genes, whether it's PRF1 or PFR1.2, again, all connected through speciation events. And then this MPEG1 gene, all connected through speciation events. So when you see alpha hemoglobin and beta hemoglobin, those are two members of the same gene family. It's actually a much larger family, the globin genes. But alpha hemoglobin and beta hemoglobin are two different genes, part of the same gene family, and they've been given names because of that. But they are paralogs of one another, and they're found in the same genome. So any two genes that are homologous, if they're found in the same genome, must, by definition, be paralogous to one another. However, once we start going across other species, we'd have different ones. So gene C6 in the human and gene C6 in the mouse are orthologous because they connect at the speciation event. But if we were to compare gene C6 in the mouse to, say, PRF1 in the humans, they are orthologous because they don't connect back here until we get back to that ancient gene duplication event.